Hi, welcome to Chapter 1 of Thermodynamics, which is the introduction and basic concepts. The next slide shows the objective of the lesson, which you can actually go through by yourself. Chapter 1.1 Thermodynamics and Energy. So, what is thermodynamics? It's a science of energy. Energy is the ability to cause changes. Usually, you can feel energy, but you can't see energy, right? So the word actually thermodynamics originates from a Greek word, which term is actually heat and dynamics is the power. So next concept is actually the conservation of energy principle. Now remember, at all time, energy changes from one form to the other. It cannot be created or destroyed. So example, can you see here? You have potential energy at the unit of 10 units up here. And when you start moving, the potential energy decreases and the kinetic increases. When it achieves to one point where the potential, which is due to height, reduces to 0 and kinetic to the maximum. So you have 10 units here, the kinetic at the bottom will be 10 units. So this is the first law of thermodynamics, which actually talks about the quantity of energy itself and the conservation of energy principle. So the second law of thermodynamics speaks about the quality of energy. The quality of energy. There will be a chapter just dedicated for second law of thermodynamics. We will go through in detail. So second law of thermodynamics also says that energy moves in certain direction. Okay. So that's about the first law and second law. Now let's move to our classical thermodynamics, which is the macroscopic approach and microscopic approach. Okay, macroscopic is a study of thermodynamics that does not require a knowledge of behavior of individual particle. It's more of like overall, the whole thing, the macro part of it. Whereas the microscopic is based on the average behavior of large group of individual particles. You look at particulate. Okay, good example of conservation of energy from the previous slide. Energy in 5 units, energy out 4 units, energy 1 stored. So at the end of the day, when you look at energy in equals to energy out for this sumo wrestler, you will see 5 went in, 1 retained in the body and 4 went out. So 1 plus 4 is 5. And now this is the second law of thermodynamics. If you look, hot coffee, which is at 70 degrees, and then we put the hot cup of coffee in a cold environment at 20 degrees, you will see that the heat travels in certain direction, not all the direction, in certain direction, which is from the hot to cold. Now the application of thermodynamics, it is just everywhere around you. You yourself is a thermodynamic system. So you're at home, you're off, your school, your office, the car that you drive, the electricity that's being generated in your house, the air conditioning system, every single thing is actually thermodynamics. That includes also your body. Your body itself is a thermodynamics system. Where food goes in, the energy from the food is converted into energy that make your muscle to move. Right? Okay, so that is the application. Is just way too much. Now I'm moving on to chapter 1.2 from the textbook. So in chapter 1.2, they're discussing about the importance of dimensions and unit. So any physical quantity can be characterized by dimension. Let me just revisit the textbook. So we have done this part of it. You can just go through. What I've done is I've just like breeze through, so you can go in detail and read them. You must actually read and understand it better. So 1.2, okay, any physical quantities can be characterized by dimension. So what is dimension? You have done this in your physics before. Probably the coverage of physics is much lesser than what we're going to do here. So length, the unit for dimension length is meter, for mass is kilogram, for time is second, for temperature is Kelvin. Probably up to here was a common thing that you have done before, but for electric is ampere, maybe you have seen. For light is candela, and for matter is mole. You see these a lot in chemistry. Now coming back to that, each dimension will have its own unit. Of course, you also can have primary unit prefixes to the unit. We'll come to that later. Some basic length such as meter, defined by the dimension of mass m and length L, time t and temperature T are selected primary. They are fundamental dimensions. Yeah, while velocity, energy, they are secondary. It means they are derived dimensions. Yeah, so these are mostly your primary dimensions. Anything that is combination like ms, -1, these are all secondary, derived. Or Newton is also derived. Newton is from kilogram meter second -2, right? So it's actually derived. So we have two systems here, which is the SI system and English system. We do not look at English system in this syllabus. We only concentrate on the metric system. So make sure the textbook that you purchase is for SI unit. Yeah. Okay. So this is prefixes. You see, why is prefixes created? When there are too many zeros, you may just miss some of the zeros. So instead of writing so many zeros at one time, what do? You just use the prefix. So we have tera, giga, mega, kilo, hecto, deca, deci, centimeter, milli, micro, nano, and pico. And this list continues below here, and this list also increases. Yeah. So what is covered here is only this part. Now, so this is some of the English and SI unit. Okay, since we are not covering English unit, but then still I will just explain to you, yeah, what is the difference. Sometimes you can get confused. Yeah, can you see this LBM? This is LBM, which is pound mass, mass, which is actually equivalent to your SI unit kilogram, whereas LBF, the one with the F there, is actually equivalent to your Newton. Okay, so this is pound force, this is pound mass. Yeah, so how do you get Newton? Newton is mass times acceleration. Yeah, so your weight is actually force. Weight is known as force. So in your normal daily life, weight is not mass. Yeah, we are actually using a wrong term. Mass is kilogram. Weight is actually a form of force. Yeah, weight is actually kilogram, Newton. Weight is Newton. How do you get weight? Mass times gravity. Okay, so that is some of the explanation here. So feet, the equivalent is actually 0.3048 mass. Yeah. Now coming back to weight, remember what I told you? Yeah. If you weigh yourself on moon, if your mass is 60 in moon, yeah, 60 units, on earth your mass will also be 60. The only thing that changes is the weight. Yeah, the weight, your weight on moon will be much lesser compared to your weight on earth, because weight is mass times gravity. It's influenced by the gravity. Yeah. Okay, now let's move on to specific weight, which is given by we have the rho equals to what is this? I forgot. Yeah, anyway, it's rho g. Yeah, this is the specific weight. Yeah. Okay, so do not look at the English unit. You only concentrate on your on your SI unit. Yeah, so you know this thing is very not common. Yeah, kilogram F is actually your Newton. Yeah, we always use Newton, right? Newton is equivalent to kilogram meter second -2. Yeah, kilogram F is actually in a way equivalent to your pound force, LBF. Okay, so don't worry much about it. You just stick to your Newton. Okay, dimensional homogeneity. You see, when you want to solve your equation, yeah, you have your equation sign, right? Okay, example, force equals to MA. You must make sure that the dimensions on the left side and on the right side must be same. So if this is Newton, this side will also give you Newton. Yeah, so what is Newton? Is kilogram meter second -2, right? So what is mass? Kilogram. What is A? A is meter second -2. Can you see that or not? On the left side and on the right side, it will be the same unit. This is called the dimensional homogeneity. If it's not homogeneous, you must convert it to homogeneous. Once again, pay attention. we do not look at as non-SI. Yeah? All the questions in this text, in this syllabus is SI. Okay, so that's done. Okay, this is just nothing. This is just showing some pictures, which weight is actually mg. Your unit is Newton. Remember, mass times gravity. Yeah, mass times gravity. So the mass here is in gram. You need to convert it to kilogram. This is the conversion. Can you see? Yeah. Okay. So you get your Newton, because Newton's formula is actually mass times gravity. Can you see? This is your conversion. Yeah, this is your conversion. Okay, you cancel your gram, leaving you with kilogram. Okay, and then you have your meter per second. So kilogram meter per second square is actually equivalent to 1 Newton. So at the end of the day, meter per second cancel, meter per second cancel, you have your kilogram cancel, leaving you with only Newton. Okay, so this is conversion of unit. Okay, it's kind of like important. You see, everything gets cancelled off, right, leaving you with Newton. Okay, so we have come to the end of chapter subchapter 1 and subchapter 1.2. I'm just going to discuss an example before I wind up this video. Yeah, so let's look at this example. This example is from your textbook that you have with you. Okay, so let's look at example 1.1. Yeah, okay, a school is paying about 0.12 cents per kilowatt per hour for electric power. To reduce its bill, the school installed a wind turbine, yeah, with a rated power of 30 kilowatt. If the turbine operates 2,200 hours per year at the rated power, determine the amount of electric power generated by the wind turbine and the money saved by the school. Yeah, so total, and so we are going to calculate this. Yeah, we're going to see how much they have actually reduced. Yeah, okay, so a wind turbine is installed to generate electricity. The amount of energy generated and saved, money saved per year to be determined. So the analysis would be 30 kilowatt or 30 kilojoule per second. Yeah, so 30 kilowatt is actually equivalent to 30 kilojoule per second, and the amount of electric generated per year becomes 30 kilowatt multiplied with 2,200. It's given in the question. Yeah, so you just multiply. What do you get? 66,000 kilowatt per hour. And the rating would be, the charges would be 0.12 cents per kilowatt per hour. Just you need to multiply. So how much has the school saved? $7,920. Yeah, similarly, like in Malaysia, in your house itself, you can actually install solar power. Yeah, literally solar is free form of energy for you, so you can actually convert the solar to money. Okay, so with that, I'm ending this subchapter. I'll see you in the next video. Thank you.